This is fourth method from chlorobenzene or bromobenzene, halobenzene. Halobenzene directly not converted into benzene. So, here in this one we have two methods again by using RMGX, by using RMGX. RMGX is called Grignard's reagent, Grignard's reagent, Grignard's reagent. So, this chlorobenzene or bromobenzene, this chlorobenzene when it is treated with magnesium dry ether, what we get here, this is converted into phenyl magnesium chloride. This is a chlorobenzene, this is a chlorobenzene and this is a phenyl magnesium chloride, phenyl magnesium chloride. This phenyl magnesium chloride when it is treated with water or in any acidic compound, water or ethyl alcohol, this is a C6H5 minus pH minus, it is a strong base and a strong nucleophile, it abstract H plus. So, we get this is a benzene, that is C6H6 is formed and plus the byproduct is MgOHCl. C, this is B, and also this is converted into what, benzene diazonium chloride. So, this is converted into benzene diazonium chloride by using benzene diazonium chloride, by using benzene diazonium chloride, benzene diazonium chloride, benzene diazonium chloride. So, how benzene diazonium chloride? Sir, actually this is starting from aniline, this is starting from aniline. Aniline is treated with, aniline is subjected to diazotization, NaNO2 plus HCl, 0 to 5 degrees Celsius. What happens? Here we get benzene diazonium chloride, N2 plus Cl minus. This is called benzene diazonium chloride. This benzene diazonium chloride, so when it is treated with benzene diazonium chloride, when it is treated with ethyl alcohol or when it is treated with H3PO3 or it is treated with sodium stannite. So, this is benzene diazonium chloride is converted into benzene plus N2 plus ethyl alcohol is converted into acetaldehyde, or otherwise H3PO4 3 is converted into H3PO4. So, this is what, this is a preparation of benzene from benzene diazonium chloride and also by using RMGX. Next, fifth one, this is from phenol, this is from phenol, This is a phenol. When phenol is heated with zinc dust, when phenol is treated with zinc dust, so what we get here, it is benzene plus ZnO. This is a benzene. This is a phenol. Phenol is heated with zinc dust, we get benzene. Next, sixth one, from benzoic acid and its salt. This is nothing but decarboxylation. This is nothing but decarboxylation. When benzoic acid, sodium benzoate or sodium benzoic acid or sodium benzoate, this is a sodium benzoate, when it is treated with soda lime, NaOH plus CaO, soda lime, decarboxylation takes place. Already we have discussed this mechanism in alkanes. So, decarboxylation takes place, elimination of this one takes place. So, we get a benzene plus Na2CO3, This is benzoic acid, this is from phenol. So, next one, this is from sulfonic acid, from benzene sulfonic acid, This is the benzene sulfonic acid. This is a benzene sulfonic acid, benzene sulfonic acid. Benzene sulfonic acid, when it is treated with water, subjected to hydrolysis, actually it is a reversible reaction. So, we get this is a benzene plus sulfuric acid. If we treat with the excess of concentrated sulfuric acid, this reaction favors backward reaction. If we use dilute, then this is benzene sulfonic acid is converted into benzene. These are the preparation methods of benzene. This preparation methods of benzene, it is finished. So, after the preparation methods of benzene, now let us discuss that is chemical properties of benzene. Chemical properties of benzene. Chemical properties of benzene and also aromatic hydrocarbons. Then chemical properties. Chemical properties. Chemical properties. Here in this one benzene, first of all, before going to discuss that chemical properties, we are going to discuss one more point here. The carbon hybridization is sp2. This one is also 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 sp2. Number of carbon atoms are 6. 6 carbon atoms. Each carbon having one pi bond. If any carbon, if it contains one pi bond, that undergoes sp2. If any carbon it contains two pi bonds, it undergoes sp hybridization. If there is 0 pi bonds, then that carbon undergoes sp3 hybridization. sp3 hybridization. If you observe this one, this benzene 1 pi bond sp2, this benzene, this carbon 1 pi bond sp2, this carbon 1 pi bond sp2, this carbon 1 pi bond sp2, carbon 1 pi bond sp2. That means all carbon atoms undergoes sp2 hybridization. Number of sp2 hybrid orbitals, how many? That is 6 into 3, 18. Number of pure orbitals. Number of pure orbitals means which do not undergoes hybridization. Each sp2 is having one pure p orbital. And hydrogen, this is also pure orbital. That means it is having s orbital. That means here each, this is 6 from sp2 hybrid orbitals and 6 hydrogens. Total kitna? 12. 18 sp2 hybrid orbitals and pure orbitals are 12. Next, number of sigma bonds. Number of sigma bonds, here 6 hydrogens, 6 plus 6, that is 12 sigma bonds. And number of pi bonds, here number of pi bonds are 3. So, this is regarding, and here, and the benzene resonance energy, here the carbon-carbon bond length is 1.39 angstroms. In this one, if you observe C double bond C bond length is 1.34 angstroms. Generally, this is in alkenes. Whereas in alkanes, C is a single bond C, this is alkane. In alkanes, that is bond length is 1.54 angstroms. Whereas in benzene, carbon-carbon bond length is 1.39 angstroms. That means in benzene we have double bond and also single bond, but this double bond and single bond is not constant between any two carbon atoms, that is always migrated from one position to the another position. So, we get this one, this is a resonating structures 1, 2, 3, 4, 5, 6, this is 1, 2, 3, 4, 5, 6, here double bond, the position of double bond is migrated. So, therefore, double bond is not constant, pi bond is not constant between any two carbon atoms, that is always migrated from one position to the another position. That means here we get like this way. This is a resonating structure of benzene. This is the resonating structure of benzene. This is resonance hybrid. So, now we are going to discuss, that is chemical properties. Actually, benzene undergoes which type of reaction, which type of reactions are possible, which type of reactions are not possible, that we are going to discuss now. So, first of all, here chemical properties of benzene. Benzene undergoes, here this is double bond, Here benzene, it is having pi electron density above the ring and below the ring, above the plane and below the plane. Here electron density is more, therefore this itself acts as a nucleophile. This self acts as a nucleophile. Benzene, acetylene, alkynes and alkenes all acts as a nucleophile. Therefore, this one undergoes electrophilic substitution reactions. Electrophilic substitution reaction. That means not only benzene, aromatic compounds undergoes electrophilic substitution reactions. Sir, why do not undergoes addition reaction? Under normal conditions, suppose if it undergoes addition reactions, so what happens if it undergoes addition reaction? Let us consider E and U. So, it is an unsaturated compound, even though it is an unsaturated compound. So, why do not undergoes addition reaction? Suppose if it undergoes addition reaction, it loses its aromaticity. So, this is aromatic compound, this is a non-aromatic compound, this is aromatic compound and it is a non-aromatic compound. Therefore, under normal condition, do not undergoes addition reactions. To retain their aromatic character, so these aromatic compounds undergoes electrophilic substitution reactions. Now, the chemical properties of aromatic hydrocarbons are chemical properties of benzene. Chemical properties of aromatic hydrocarbons are chemical properties of benzene. Here already now we discussed, that is benzene do not undergoes addition reaction under normal conditions, but benzene undergoes electrophilic substitution reaction. Now, that is aromatic electrophilic substitution reactions, that is electrophilic substitution reactions. Substitution reaction means the reaction in which one group or one atom is substituted by another group or another atom, that is called a substitution reaction. If one electrophile is substituted by another electrophile, then it is called electrophilic substitution reaction. Benzene అనేది electrophilic substitution reaction లో participate అవుతుంది. ఇందులో in electrophilic substitution reaction, we have general mechanism. Suppose if we take this is a benzene, here it is treated with reagent, it is having electrophilic part and a nucleophilic part. So, what happens here, we get this is E plus HNU. Now, see here the mechanism. In electrophilic substitution reactions, this one takes place in 3 steps. First one is generation of electrophile. Second one is formation of sigma complex. Third one is loss of H plus. Now, so first of all, generation of electrophile. So, electrophile already generated, this we will discuss in different reactions. First of all, formation of sigma complex, that is formation of sigma complex. This sigma complex, it is also called erinium ion. Sigma complex, this is also nothing but erinium ion. In this one, what happens? This is a benzene. Already electrophile is generated. Now, this electrophile attacks on benzene, even though it attacks on benzene, but we are indicating the arrow mark from benzene to electrophile. Why? Because we have to always indicate the arrow mark from high electron density to low electron density. So, what happens here? This is here, it is double bond, here it is double bond. This we have H, this we have E, and here it is positive charge. This is cyclohexadienal cation. this cyclohexadinyl cation. Now the formed cyclohexadinyl cation, now this is stabilized by resonance. This is stabilized by resonance or delocalization of electrons. Now this is pi bond, this is pi bond, this pi bond. Now this pi bond is migrated here. Here in this one, what we get here? This is double bond, here double bond, this is H, this is E, here it is positive charge. Now again this pi bond is migrated here. So we get here, this is double bond, this is H, this is E, here it is positive charge. This is cyclohexadinyl cation, this is cyclohexadinyl cation, that is also cyclohexadinyl cation. That means this, if you observe this one, the positive charge first of all here, then here, then here. That means the positive charge is delocalized between these carbon atoms only. Therefore, we can write the total molecule, this one we can write like this. So here this is positive charge, H and E, H and E. We should not complete this dotted line, dotted dot. Why? Because this positive charge is delocalized from this carbon to this carbon only. So this is called rhenium ion. Rhenium ion. This is also called cyclohexadinyl cation. This is also nothing but cyclohexadinyl cation, or this is nothing but sigma complex. This is nothing but sigma complex. Sigma complex means, here why it is called sigma complex? This is a complex molecule and electrophile is attached to the aromatic compound by sigma bond. Therefore, this is called sigma complex. Here this is a slow step. Generally it is a slow step. Slow step, it is a rate determining step. Slow step is a rate determining step. So third one, then the last stage, this is slow step and rate determining step. The last step is loss of H plus. Loss of H plus. So what happens here? So take this rhenium ion, this double bond, this is H, this is E, and it is positive charge. And the next one, in this last step, this is a generally this is a fast step. This is a fast step. Here this is nothing but a base. This is nothing but a base. This base abstract this H plus and this bond is migrated. Here we get this compound electrophile substituted arene. Electrophile substituted arene. So this is nothing but electrophilic substitution reaction. Aromatic electrophilic substitution reaction, this one takes place in 3 steps. Generally we are considering 2 steps. Generally this is not considering as a step, or otherwise we consider there is no problem. Generation of electrophile, formation of sigma complex and loss of H plus. Generally the formation of sigma complex is a slow step, but in all aromatic electrophilic substitution reaction this is not a slow step, but some reactions this is not a maximum reaction, this is the formation of sigma complex or rhenium ion or cyclohexadinyl cation is a slow step. So this is a general mechanism. So after the general mechanism, now let us apply this mechanism on different types of aromatic electrophilic substitution reactions. Now that is first of all that is halogenation. That is halogenation. Let us discuss regarding halogenation. In this halogenation, first of all, this is halogenation. Halogenation. Here in this one, fluorine is more reactive than chlorine, chlorine is more reactive than bromine, bromine is more reactive than iodine. We are not considering fluorination. Why? Because that is fluorine is highly reactive and polyfluorination takes place. Therefore, that explosive reaction takes place. Therefore, we are not considering fluorination. Now, we are going to discuss that is regarding chlorination, bromination and iodination. Let us take this is a benzene. Here it is a benzene. Benzene is treated with chlorine in the presence of Lewis acid. In the presence of Lewis acid. Lewis acid, let us take that is AlCl3, anhydrous AlCl3. or we can use AlCl3 or FeCl3. This is nothing but Fe by Cl2. We can use Fe by Cl2 or ZnCl2. So we can use Lewis acids. So on heating, so what we get? We get chlorobenzene. We get what? Chlorobenzene. This is a benzene. This is a chlorobenzene. This is a benzene and this is a chlorobenzene. Now what happens here? Again mechanism. The first step is formation of or generation of electrophile. Generation of electrophile. Generation of electrophile. The generation of electrophile, how electrophile is generated here? So first of all, the Cl and Cl plus AlCl3, it is having vacant orbital. This chlorine, it is having lone pairs. How many? Each chlorine is having 3 lone pairs. This one donates, and this is converted into AlCl4 minus plus Cl plus. This chloronium ion, this is a chloronium ion, it is a chloronium ion, it is a electrophile. So after the formation of the cell, suppose if you take Fe plus Cl2, sir, what happens? Fe plus Cl2, it is converted into FeCl3. The formed FeCl3 reacts with Cl2. This is converted into FeCl4 minus plus Cl plus. This is a chloronium ion, is a electrophile. This is a electrophile. This is a electrophile. The formed chloronium electrophile, the second step is that is formation of sigma complex. Formation of sigma complex. Formation of sigma complex. So the formed chloronium, now it attacks Cl plus. Now it attacks Cl plus. So we have to indicate arrow mark from here to here. So what we get, this is here double bond, here this is positive charge, this is H, this is Cl. Again this is stabilized by resonance, already we have discussed general mechanism, that means the positive charge is migrated from here to here, oscillated. This is positive charge, this is H, this is Cl. In this one, this is a slow step, this is a slow step, and this is a rate determining step. Third one is, that is loss of H plus. Loss of H plus. The loss of H plus, so that take that is chloronium, that is erinium ion, this is this is plus, and this is H, this is Cl. In this one we have AlCl4 minus, that AlCl4 minus acts as a base. Now it abstracts this H plus, this bond is migrated. So now we get this is double bond, here it is Cl. This is a chlorobenzene. And that is a slow step and rate determining step. This is a fast step. This is a fast step. In this mechanism, your important point is primary kinetic isotopic effect. That is primary kinetic isotopic effect. Isotopic effect. Here in this one, primary kinetic isotopic effect is absent. That means the rate of C6 is approximately equal to C6D6 is approximately equal to C6T6. That means the rate determining step, this is not a rate determining step. In chlorination, there is no primary kinetic isotopic effect. No primary kinetic isotopic effect is absent. Primary kinetic isotopic effect is, primary kinetic isotopic effect is absent. Primary kinetic isotopic effect absent in chlorination, but the primary kinetic isotopic effect observed in iodination. This is what, this is halogenation. In halogenation we are discussing, that is chlorination. So this is generation of electrophile. Here the electrophile is chloronium electrophile. So that is this is the formation of sigma complex or erinium ion, that is a slow step, and loss of H plus, that is a fast step. Here it is not having primary kinetic isotopic effect. Suppose if it is treated with C6H6 and C6D6 and C6T6, the rate is approximately same. That means primary kinetic isotopic effect is absent. Next one is here iodination. Now we are going to discuss, that is regarding iodination. So, in iodination we can observe primary kinetic isotopic effect. Iodination we can observe, that is primary kinetic isotopic effect. That is especially important. Suppose iodination. In iodination what happens? Take benzene and treat with iodine. Actually here we get this is iodobenzene, this is iodobenzene, this is a reversible reaction. It is a reversible reaction. This is benzene and iodobenzene, it is a reversible reaction. In this one, if you observe the mechanism, that is I2 here, so we get this structure. This is rhenium ion, this is iodine, this is H, here it is positive charge, this is rhenium ion, and let us consider this is K1 and this is K minus 1 and this is K2 and this is what we get, this is iodobenzene. Experimentally observed that is K minus 1, it is greater than K2. This indicates this is a slow step. That means this is a slow step. That means loss of H plus is a slow step. Therefore, it is having primary kinetic isotopic effect. That means C6H6 is greater than C6D6 is greater than C6T6. This is reactivity, the rate of reactivity towards iodination. Whereas in chlorination, primary kinetic isotopic effect is absent, whereas in iodination, primary kinetic isotopic effect is present. This is important for all entrance examination point of view. So, why? Because this is the loss of H plus involves that is slow step, therefore, this is having primary kinetic isotopic effect. This is iodination. So, after iodination, chlorination, bromination and iodination. After iodination, now let us discuss, that is nitration. This is the second one. Introducing of NO2 plus. This is called nitronium electrophile. In this nitronium electrophile, for the generation of nitronium electrophile, we are using nitration mixture. First one is nitration mixture. So, the nitration mixture is 1:1 ratio of concentrated HNO3 and concentrated H2SO4. 1:1 ratio of concentrated HNO3 and concentrated H2SO4 is called nitration mixture. This nitration mixture produces nitronium electrophile, or otherwise we can also use nitronium perchlorate. This can also be, we can use nitronium perchlorate. Nitronium perchlorate is NO2 plus ClO4 minus. This is nitronium perchlorate. Or otherwise we can also use nitronium fluoroborate. Nitronium fluoroborate, that is NO2 plus BF4 minus. This is nitronium fluoroborate. And also we have so many nitration reagents, that is NO2 plus BF4 minus nitronium perchlorate. Nitronium acetate is also there, that is CH3COO minus and NO2 plus. So, generally this one, these are used for introducing of NO2 plus. Let us take example, this is a benzene. It is treated with nitration mixture, that is a concentrated HNO3 plus concentrated H2SO4, that is below 60 degrees Celsius. What happens? We get nitrobenzene. Again mechanism. Mechanism is, first one is generation of electrophile. Electrophile, how? Again, this is an aromatic electrophilic substitution reaction. Generation of electrophile, that is electrophile, how generation electrophile is generated. This is HO nitric acid HNO3 double bond O, this is HNO3 plus H2SO4, HO S double bond O OH, this is H2SO4. So what happens here in this one, this is having hydrogen. Now this is oxygen lone pair, and this one abstract this H plus. We get that is HOH, here it is plus, this is N double bond O, here it is O. Then that is the byproduct is HSO4 minus. Then loss of H2O, what we get, this is NO2 plus, nitronium electrophile. This nitronium electrophile is produced. In this one, this is HNO3 and H2SO4, this sulfuric acid, it acts as an acid. Why? Because it is proton donor and it acts as a base, and it is proton acceptor. After the formation of nitronium electrophile, the second step is, that is formation of sigma complex. This is also called arenium ion. What happens? This is a benzene. Now again we are attacking what? NO2 plus. This is NO2 plus. Okay, here the pi electrons. So this one, here we get, this is double bond, so not double bond. Here this is H, this is NO2 and it is plus. This is stabilized by delocalization of pi electrons. This is H, this is NO2, like this. Generally it is a slow step. Again it is a slow step. Rate determining step. Third one is loss of H plus. So take this sigma complex. This is H, this is NO2, here it is having positive charge. Now that HSO4 minus, abstract this H plus, this is a fast step, and here the bond is migrated here. This we get a double bond, this is NO2. So this is nitrobenzene is formed. This is the first step, and last this is. And here important point here in this one, that is again primary kinetic isotopic effect. If you observe this one, the formation of sigma complex is a slow step. Not loss of H plus is a slow step, whereas in iodination loss of H plus is a slow step. But here the formation of sigma complex is a slow step. Therefore, this is also not having isotopic effect. Primary kinetic isotopic effect is absent. Primary kinetic isotopic effect is absent. That means C6H6 is approximately equal to C6D6 is approximately equal to C6T6. This is reaction towards that is which one? Towards nitration. This is nitration. After nitration, next one is sulfonation. In this sulfonation, it is having, that is primary kinetic isotopic effect. It is having primary kinetic isotopic effect. That is sulfonation. So this is the next one is, this is third one, this is sulfonation. For sulfonation, we are using fuming sulfuric acid. So fuming sulfuric acid is nothing but the mixture of concentrated H2SO4 plus SO3. This is called fuming sulfuric acid, or otherwise concentrated sulfuric acid, or we also use chlorosulfonic acid. Again, it is also having 3 steps, but I am writing 3 steps in a single right. That is generation of electrophile. This is H2 concentrated H2SO4. So what we have, this is formation of sigma complex. This is sigma. This is H. This is SO3 minus. Here to here, we have positive charge. And next one, that is again this is that is H plus, loss of H plus, again we have this one SO3 minus, then addition of H plus, so we get a benzene sulfonic acid, again it is K1, this is K minus 1, this is K2, again K minus 1 is greater than K2, that means this is a slow step, so that means loss of H plus is a slow step, therefore it is a rate determining step, therefore it is also, it is having this kinetic isotopic effect, kinetic isotopic effect means that is C6H6 is greater than C6D6 is greater than C6T6. That means kinetic isotopic effect we can observe only in iodination and sulfonation, but the remaining reaction, that is kinetic isotopic effect, is absent. This is sulfonation. So after that sulfonation, next we have that is Friedel-Crafts alkylation and also Friedel-Crafts acylation. These two reactions are important. First of all, Friedel-Crafts alkylation. Is very, very important. So when benzene is treated with alkyl halide RX in the presence of Lewis acid, on heating we get alkyl benzene. We can also use other compounds, that is alkenes also we can use, alcohols also use for generation of alkyl carbocation. In this one again same mechanism, that is generation of electrophile. So first of all, actually what happens in this electrophile, for example if you take benzene when it is treated with CH3Cl in the presence of AlCl3, what happens? Here we get this is toluene is formed. This is a toluene. In this one mechanism, just only two steps mechanism, that is CH3Cl plus AlCl3. This AlCl3 abstract Cl, this is converted into AlCl4 minus plus CH3 plus. This carbocation, it acts as an electrophile. Now this one attacks on benzene, we get a toluene. Suppose if we take ethyl chloride, that is CH3CH2Cl in the presence of AlCl3, anhydrous AlCl3. So what we get? This is ethyl benzene, CH2CH3. Again in this one, that is CH3CH2Cl plus AlCl3. So this is converted into AlCl4 minus plus CH3CH2 plus. Now this is a electrophile. So after this one, suppose if we take benzene plus CH3CH2Cl in the presence of anhydrous AlCl3. Everybody is thinking that this N-propyl benzene is formed. But in this reaction, N-propyl benzene is not formed. So which one is formed in this reaction? That is isopropyl benzene is formed. Isopropyl benzene. This is isopropyl benzene. This isopropyl benzene is nothing but this is called cumene. Cumene is formed. Sir, how? Just we are going to discuss only generation of electrophile, not the remaining thing. So what happens in this one? CH3CH2Cl plus AlCl3 plus AlCl4 minus. plus CH3 CH2 CH2 plus. This is the primary carbocation. This primary carbocation, it is less stable. So what happens here? This one H 1,2 hydride shift takes place. 1,2 hydride shift takes place. So we get this isopropyl carbocation is formed, CH3CH plus CH3. This is a secondary carbocation. Now the secondary carbocation attacks on benzene, we get isopropyl benzene. So after isopropyl benzene, now suppose benzene plus CH3 CH CH3 CH2 Cl. The name of this compound is isobutyl chloride. Isobutyl chloride in the presence of AlCl3. If you observe, that's the first step mechanism, only the total not mechanism, not required total mechanism. In this one CH3 CH CH3 CH2Cl plus AlCl3. AlCl3 plus Cl, we get AlCl4 minus CH3 CH3. This is CH2 plus AlCl4 minus. This is again 1,2 hydride shift. 1,2 hydride shift. So what we get? CH3 CCH3 CH3. This is a tertiary carbocation. This tertiary carbocation is formed. Again 1,2 hydride shift. That means any carbocation is formed. Remember one thing, that is there may be possibility of rearrangement takes place. Now this one attacks on benzene. So we get this compound. This is a tertiary butyl benzene. This is a tertiary butyl benzene. So not we get this compound, that is CH2 CH CH3 CH3. This is not formed. That one is formed. Why? Because here rearrangement is taking place. Now we are going to discuss some more examples in this one. Suppose benzene plus chlorobenzene plus AlCl3. Here reaction does not take place. Reaction does not take place. Why? Because this is in chlorobenzene. This is chlorine. It is having, this is having double bond character. This is having double bond character. This never forms, that is phenyl cation. This is unstable. Therefore, chlorination, this reaction does not take place. Suppose if you take benzene plus vinyl chloride CH2Cl in the presence of AlCl3, in the presence of AlCl3. Here also reaction does not take place. That means CH2 double bond CHCl plus AlCl3. So vinyl cation, that is vinyl cation is not formed. CH2 double bond CH, this is unstable. This cation is not formed. Therefore, that reaction does not take place. Suppose if you take benzene plus allyl chloride, this is benzene plus allyl chloride in the presence of AlCl3, the presence of AlCl3. So we get this is CH2 single bond CH double bond CH2. So here in this one mechanism, that is CH2 double bond CH2 Cl, that is AlCl3 CH2 double bond CH2 plus, this is stabilized by resonance. So in this one, so this is that reaction, that compound is formed. Now I will give, let us discuss one more example, superb example. So ring expansion takes place. So where ring expansion takes place? See here. So this is a benzene. A benzene is treated with this compound. Which compound? Here. So this is Cl. This is Cl. So this is Cl. This is CH3. If we treat with AlCl3, so which compound is formed? This is our question. Which compound is formed? Now see here the mechanism. So not total mechanism, just only generation of electrophile we need here. Here this is Cl plus AlCl3. AlCl3 plus Cl, AlCl4 minus. Next, this is carbocation is formed. this 𝗂𝗏 is formed. So after this 𝗂𝗏, in this one ring expansion takes place, that is 1,2 bond shift, 1,2 bond shift, 1,2 bond shift takes place. This is the 𝗂𝗏. This is nothing but, this is a 6-membered, this is a 6-membered ring, and it is a secondary 𝗂𝗏. And again 1,2 hydride shift takes place, 1,2 hydride shift. So 1,2 hydride shift takes place. So what we get? This is 𝗂𝗏, this is a tertiary 𝗂𝗏 is formed. So in this one 1,2 bond shift, 5-membered is converted into 6-membered. Similarly 1,2 hydride shift, that is tertiary secondary is converted into tertiary. Now the formed electrophile is that one, that is major product of this reaction is, this is the major product, this is the major product, this is the major product is formed in Friedel-Crafts alkylation. So here in this one, if we observe, that is benzene, this compound. So 1,2 bond is shifting. Why it is 1,2 bond shift? But ring expansion, 5-membered is converted into 6-membered. After that one 1,2 hydride shift, that is tertiary 𝗂𝗏, secondary 𝗂𝗏 is converted into tertiary 𝗂𝗏. So this is Friedel-Crafts alkylation. Friedel-Crafts alkylation. In this one Friedel-Crafts alkylation, we are used alkyl halides. Sir, if we use alkenes, what happens? Electrophile is generated or not? Yes, 100% electrophile is generated. So how alkenes are used in Friedel-Crafts alkylation? See here, this is a benzene. Benzene, it is treated with CH3, CH double bond CH2. In the presence of HF, what happens? We get isopropyl benzene. In this mechanism, CH3, CH double bond CH2 plus H plus. Where it is coming from? HF, it gives H plus. Then this is an electrophilic addition reaction. So what we get? This is CH3, CH plus, this is CH3. This is isopropyl carbocation is formed. This isopropyl carbocation, it acts as an electrophile. Now it attacks on benzene. So we get what? This is isopropyl benzene, that is a cumene is a formed. This is a cumene is a formed. Now we have one doubt, sir, after the addition of H plus, why F minus do not attacks? Why? Because F minus is a poor nucleophile. Suppose instead of HF, if you take HCl, yes, 100% reaction takes place, that is H and that is alkyl chloride, that is isopropyl chloride is formed. So here HF, that means alkene also used for the alkylation in Friedel-Crafts reaction. So after this one, sir, if we, what happens, sir, if we use alcohols? Yes, alcohols, we can also use alcohols. 100% we can use alcohols. Yes, alcohols also used for Friedel-Crafts alkylation. Now see here, this is a benzene. Now this is treated with cyclopentanol. This is treated with cyclopentanol. In the presence of BF3, what happens? This is a cyclopentyl benzene is formed. Now see here mechanism. In this mechanism, that is, this is cyclopentanol. This cyclopentanol, here it is treated with BF3. Oxygen is having lone pair. So this is converted into, okay, this is converted into OH. Here it is plus. This is BF3 minus. Then loss of this one. So we get carbocation. This carbocation, it reacts with benzene. So we get that is again cyclopentyl benzene is formed. Here we can also use alcohols. So benzene, it is treated with alcohols. In the presence of Lewis acid, we get that is Friedel-Crafts alkylation. In Friedel-Crafts alkylation, we can use alkyl halides, alkenes, and also alcohols. So this is Friedel-Crafts alkylation. So after this one, Friedel-Crafts acylation. Friedel-Crafts acylation. Acylation means introducing of acyl group. Again, benzene is treated with acetyl chloride or acetic anhydride CH3 C double bond O C double bond O CH3. In the presence of Lewis acid, anhydrous Lewis acid, we get a acyl benzene, that is C double bond O CH3. In this one, here again let us discuss the mechanism. CH3 C double bond O Cl plus AlCl3. So, we get, that is CH3 C double bond O plus AlCl4 minus. This one also gives, that is acyl carbocation. This we get, this is a benzene, this is called acetophenone. Similarly, this benzene, if it is treated with CH3 this is CH3 C double bond O Cl in the presence of AlCl3. So, everybody is thinking that this compound is formed C double bond O CCH3, this compound is not formed. So, this is a special example. In this one mechanism, first of all CH3 CH3 C double bond O Cl plus AlCl3 plus Cl, AlCl4 minus is formed, AlCl4 minus plus CH3 CH3 C double bond O plus is formed. So, this is less stable. So, what happens here? Loss of CO, CH3 C double bond CH3 this is carbocation. This is more stable when compared to this one. Therefore, loss of CO takes place after the formation of this tertiary butyl carbocation. This tertiary butyl carbocation attacks on benzene. So, we get this compound, that is tertiary butyl benzene is formed. This is nothing but Friedel-Crafts acylation. After Friedel-Crafts acylation, this is general mechanism. In Friedel-Crafts acylation, there is no primary kinetic isotopic effect. In Friedel-Crafts alkylation and Friedel-Crafts acylation, so there is no primary kinetic isotopic effect. So, only primary kinetic isotopic effect we can observe in, that is with in iodination reaction and in sulfonation reaction. So, after this one, so effect of substituent on benzene ring towards electrophilic substitution reactions. Actually, groups are classified into two types, that is activating groups and deactivating groups. Suppose NH2, NHR, NR2, OH, OR, all these are strongly activating groups. Similarly, NHC double bond OR, OC double bond OR, these are moderately activating groups. Next, R, AR, CH double bond CH2, these are weakly activating groups. Similarly, F, Cl, Br, I, these are weakly deactivating groups. These strongly activating groups, moderately activating groups, and weakly deactivating groups, and this is weakly activating groups and weakly deactivating groups. All these are ortho-para directors. Similarly, that is C triple bond N, sorry, not C double bond OH, C double bond O NH2, C double bond O Cl, C double bond O OH, all these are moderately deactivating groups, moderately deactivating groups. Similarly, C triple bond N, SO3H, NR3 plus, NO2, etc. etc. All these are strongly deactivating groups, strongly deactivating groups. These are strongly activating, these are ortho-para directors, but these two are meta directors. These two are meta directors. That means if these groups are present, electrophile attacks on ortho and para position. If that groups are present, electrophile attacks at meta position. Suppose here we have, this is a naphthalene system. In this one C double bond O, here it is NH, this group. So here it is treated with, this is treated with Feldenkrais, this is not Feldenkrais, this is treated with Cl2 by AlCl3. What happens? So on which ring it attacks? Here the electrophile is LSCl plus. This is a activating group and this is a deactivating group. This is a deactivating group and this is a activating group, and it is which director? Ortho and para director. Therefore, electrophile attacks at para position only. Here ortho position is also possible, but due to steric hindrance, this is a minor product and this is a major product. NH2 is the activating group. So here it gives electron density, it increases electron density at ortho and para position, and whereas this is a deactivating group, it decreases electron density at ortho and para position. So therefore here in this one, your electron density is more at ortho and para position. So when compared to ortho position, para position is that is electron density is more, but here steric hindrance. So due to steric, this is minor product and this is a major product. Similarly, if you observe this compound, this is C double bond O, C double bond O here. So if it is treated with again Cl2 by AlCl3, where it attacks, here it is lone pair. This one gives electron pair to the benzene ring, that means electron density increases at ortho positions and para positions. Here it is a deactivating group, this is an activating group, it increases electron density at ortho and para position. So due to at ortho position, steric hindrance is more, therefore minor product is formed. The Cl plus attacks at which position? That is a para position, that is C double bond O, and this is here this is Cl, this compound is formed. This is a major product. So here this is a activating and deactivating groups, that is very important. And one more important point here, if you observe this chlorobenzene, this chlorobenzene, here Cl it is having minus inductive effect, this is having minus inductive effect, and it is also having plus resonance effect. Minus inductive effect and plus resonance effect Cl. So this inductive effect and resonance effect, inductive effect operates reactivity and resonance effect operates orientation. Due to plus resonance effect, it is which director? This is a ortho and para director, and it is a weakly deactivating group. This is a weakly deactivating group, but it is a ortho-para director. This is a minus inductive effect. Due to minus inductive effect, the reactivity of chlorobenzene, it is less than benzene. If you observe this benzene, the reactivity of benzene is greater than chlorobenzene towards electrophilic substitution reaction. Minus inductive effect controls reactivity and plus resonance effect controls orientation, even though it is a deactivating group, but it is a ortho-para directors. And here this is a benzene, it is electrophilic substitution reaction, it is more than chlorobenzene.